All right, so here we are with the topic calculating equilibrium compositions or concentrations from an equilibrium constant. And so if you look at the information that we're given here, they tell us that we have a 250 milliliter flask and it's filled with 1.4 moles of this chemical here and 1.3 moles of this chemical here, um, hydrogen chloride. And then we have 0.6 moles of carbon tetrachloride. And they give us the chemical reaction, this balanced chemical equation. So they were nice enough to balance it for us, but we always want to double check and ensure that the stoichiometry is correct, that the coefficients are what they should be before we move forward, okay? Because if you remember, the coefficients play a part when we write the equilibrium constant expression. So we need to make sure that all of our chemical equations are balanced to begin with. So the first thing that we need to do is we need to determine our initial concentrations, because what they ask us is to calculate the equilibrium concentration of HCl. So they want the concentration of this. What is the concentration of that at equilibrium? Well, we can find that by using this, what Alex calls a reaction table, or I call it an ICE table. I for initial concentration, C for change in concentration, and E for equilibrium concentration. We can determine the equilibrium concentration, but we need to first fill out these first two rows to figure out what the mathematical expression will be that'll help us to find equilibrium concentration. So let's do that. So what is the initial concentration of this first substance here? Well, in order to find that, we have to use the information given in the problem. So here you can see that they give us the mole amount of these three substances. And they also give us the volume of the flask. So we know the volume that these mole amounts are occupying. And so because we have moles and because we have a volume that we can convert to liters, we have concentration, molar concentration. Molarity by definition is mole per liter. So if I want to find the initial concentration of CHCl3, and I'm going to represent that by putting the little knot symbol there, okay, that signifies, this right here signifies initial, then it's going to be equal to the number of moles of that I had initially divided by the volume that's occupying in liters, so that would be 0.250 liters. So when I do that math, what I have is 5.6 molar, okay? Now let's look at the next substance that we have some of initially, hydrogen chloride. What is the initial concentration of hydrogen chloride gas? Well, how many moles of it did we have initially? 1.3 moles in 0.250 liters. So if I take 1.3 and divide it by 0.250, I get 5.2 molar, okay? And our last third substance here that we have some of to begin with is carbon tetrachloride. What would be the initial concentration? Well, it would be equal to the number of moles that we begin with divided by the volume that it occupied. That's 0.6 divided by 0.25. And that is 2.4 molar. Okay? So what we have done is we have found initial concentrations of these three substances involved in this chemical reaction. So the initial concentration of CHCl3 is 5.6 molar. We don't have to worry about the units here. We could just put the value there, okay, because I know that this is referring to concentration, change in concentration, and equilibrium concentration. Hydrogen chloride, 5.2 molar, and carbon tetrachloride, 2.4. So what was the initial concentration of molecular chlorine, chlorine gas? Well, we didn't have any. How do I know? Because they stated in the problem. They say this flask is initially filled with this, this, and this. So you may be wondering, well, if we didn't have any to start with, how does this reaction proceed? Well, it's because this reaction, like most reactions, is reversible, meaning it can go in both directions. So even though we don't have any chlorine gas to begin with, we will end up with some chlorine gas because we have these products here. And there is a reverse reaction where these can produce our reactants, just like our reactants react together to produce our products, okay, to yield our products. So our next step is to determine what the change in concentration will be from the initial concentrations as we work to equilibrium concentrations. So what we've learned about equilibrium is that, well, this reaction will go in the forward and reverse directions. And depending on what the equilibrium constant for this reaction is, one direction will be favored or may be favored over the other. And eventually this reaction will come to equilibrium. And at equilibrium, the rate of the forward and reverse reactions are the same. And so essentially we have no changing concentrations. It doesn't mean that the concentrations of everything on both sides is equal. It just means that it's no longer changing. They've stabilized. So if we want to find the equilibrium concentration, we know that it's going to be different from the initial concentration by some amount, some molar amount. We're not sure what that is, but we're going to represent that change with the letter X. We're going to use algebra, okay? So if we initially have no chlorine gas, initially no chlorine at all, 0 molar here, concentration of 0. At equilibrium, I'm going to have some, obviously. Okay, I'm going to have some. It may not be a lot, but there's going to be some. So that means that the change in the concentration of chlorine from the initial concentration is going to be positive. Does that make sense? And because chlorine is a reactant, just like CHCl3, well, if I have an increase in the amount of Cl2, I'm also going to have an increase in the concentration of CHCl3. So this will also be positive. My products over here, their change in concentration will be negative. So what do we place after this, after we determine what the signs is? Well, we're going to represent the change in concentration with the letter X. We're going to use some algebra here. So the initial concentration is going to change by some amount that is represented by X. Now this is where the stoichiometry comes in. In this case, all of the coefficients are 1. But if the coefficients were not 1, we'd have to make sure that those coefficients were carried down here. Okay, so if this coefficient were 2 perhaps, we'd have to put plus 2x. But because it is 1, this is simply going to be plus x. Here we also have minus x, and here we have minus x. And so now we can derive an expression using algebra to determine what the equilibrium concentration will be. And we just combine these boxes here in each column. So 0 plus x is just simply x. 5.6 plus x is 5.6 plus x. 5.2 minus x is 5.2 minus x. 2.4 plus negative x is 2.4 minus x. So there we go. So according to our ICE table, or our reaction table, this is telling us that we can find the equilibrium concentrations for this reaction under these conditions at this temperature, as long as we know what X is. Well, guess what? There is a way to determine X. And the way that we do this is by writing and using the equilibrium constant expression. That should look very familiar. So let's write our equilibrium constant expression over here. So what is the equilibrium constant expression? Well, it's K, the equilibrium constant, and because here we have molar concentrations. Okay, we see we have molar concentrations. We're going to be using Kc. Okay, so Kc is equal to the concentration of our products, and our products are HCl and CCl4, raised to their stoichiometric coefficients, and all of the coefficients are 1. So it's simply the concentration of HCl times the concentration of CCl4 divided by the same thing for our reactants, Cl2 and CHCl3. So we have Cl2 and CHCl3. Now, how is this equilibrium constant expression going to help us solve for X? Well, if we go back and if we look at the information given here in the problem, we see that they give us K. So I know what K is, it's 1.25. I also know what the equilibrium concentrations are for every substance involved in this reaction. We have derived these mathematical expressions to represent the equilibrium concentrations. So what if I took the given K, and what if I took what the equilibrium concentration for each substance is equal to, and I place these into the equilibrium constant expression? That's exactly what we're going to do. So we're going to write that Kc, which is 1.25, so we'll substitute that. 1.25 is equal to, what is the concentration of HCl at equilibrium? Well, we wrote here that it is equal to 5.2 minus X, and this is going to be multiplied by what carbon tetrachloride is equal to at equilibrium. The concentration is equal to 2.4 minus X divided by X times 5.6 plus X. Okay, so we have our equilibrium concentrations and our Kc placed into our equilibrium constant expression. So now we just solve for X, and once we find out what X is, we can come back here and place the value for X in these expressions to find the equilibrium concentrations. All right, so let's begin to do that. So first thing we want to do is write that 1.25 is equal to, let's figure out what 5.2 times 2.4 is. 5.2 times 2.4 is 12.48 minus 5.2x minus 2.4x plus x squared over 5.6x plus x squared. Okay, next thing I want to do is bring this up by multiplying both sides by 5.6x plus x squared. So we end up with 1.25 times 5.6x plus x squared is equal to 12.48 minus, this will be 7.6x plus x squared. 5.6 times 1.25 is 7. Now notice I just write 7, but that's because it's equal to exactly 7. Now, if there were some decimals after that value, I want to make sure that I keep them. Don't round your intermediate values too early. It'll take precision away from your final answer. But this happens to be exactly 7, and I'm just going to write it as that, plus 1.25 x squared is equal to 12.48 minus 7.6x plus x squared. Now, the next thing I want to do is I want to start to rearrange what I have right now, because I want to rearrange it into this, a quadratic expression. ax squared plus bx plus c is equal to 0. The reason I want to do that is because once I have this, I can use the quadratic formula to help me to solve for x, which is exactly what we are trying to do. Okay? So to begin to rearrange it, I can take this x squared over here and bring it to the other side by subtracting x squared from both sides. So 7x plus 1.25 x squared minus x, there's a 1 in front of it, minus x squared is equal to 12.48 minus 7.6x. This becomes 0.25 x squared is equal to 12.48 minus 7.6x. Okay, let's get rid of this by adding 7.6x to both sides. And I end up with 14.6x, and this is plus 0.25 x squared is equal to 12.48. Okay, so that got rid of that here, and that got rid of that there. It will take 14.6x plus 0.25 x squared minus 12.48 is equal to nothing now on the right, 0. So let's take these two. Let's take 0.25 and put it out in front so it's positive. So we have positive 0.25 x squared, and this is a positive 14.6. So plus 14.6x minus 12.48 is equal to 0. And there we have our quadratic expression. So now that we have that, we have A is equal to 0.25. We have B is equal to 14.6, and we have C is equal to negative 12.48. We can come over and plug this into the quadratic formula. The quadratic formula is x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay? Now what you'll notice here when you look at the quadratic formula is that we have a plus or minus. So that means x is going to have two possibilities. But the good thing is one of the possibilities for x will always be impossible. So we don't have to worry about trying to decide, oh, which one is the correct possibility, because one will always be impossible. So what I'm going to do is set up two instances here where we're solving for x. One is going to be using the addition function, and the other is going to be subtraction. So I'm going to erase the minus sign here. Erase it and rewrite it. There we go. Okay, so we have our values, A, B, and C. Let's plug them in. X is equal to negative 14.6 plus the square root of 14.6 squared minus 4 times 0.25 times negative 12.48. All divided by 2 times 0.25. So then we end up with x is equal to negative 14.6 plus the square root of 14.6 squared is 213.16 minus 4 times 0.25 times negative 12.48 is negative 12.48. And then on the bottom, we have 2 times 0.25, which is going to be equal to 0.5. So now x is equal to negative 14.6 plus the square root of 213.16 plus 12.48 minus a negative becomes addition, positive. 225.64 divided by 0.5. X is equal to negative 14.6 plus the square root of that is 15.0213. Notice I didn't cut off too many decimal places. X is equal to negative 14.6 plus 15.0213 divided by 0.5. I get 0.8426. One possibility for X. For the next possibility for X, because I already did the math for this part and for this part, I'm just going to skip down to what's different. And what is different is the addition, the adding here. Okay, over here, we're not going to add, but we are going to subtract. So X is equal to negative 14.6 minus 15.0213 divided by 0.5. X is equal to negative 14.6 minus 15.0213 divided by 0.5. This is negative 59.2426. So we have here two possibilities for X. One of these is obviously wrong. The question is, which one? Well, let's go back to our original information. Let's look at HCl. Here, the concentration of HCl is going to change by negative X. Well, if X is 59 molar, then there's no way that that is possible. Well, there's not enough of anything else for that to even be possible. Well, let's look at the other way. If this is going to, the concentration of this is going to increase by plus X, and if X is negative 59, then that means that the concentration of Cl2 would be negative 59 molar. It just doesn't make sense, okay? So that is obviously the impossible answer. So if we go here, we immediately know that that is the one that's impossible, and the correct value for X will be 0.8426. Now, if we really want to check our answer, what we can do is take these values for A, B, and C and plug them into a quadratic formula calculator. Now, I don't encourage you all to do this before. Know how to work these problems, practice doing the math, but I would definitely use a quadratic formula calculator to check my answers. So let's do that. A is, what we got for A was 0.25. What we got for B was 14.6. And for C, we had negative 12.48. So let's hit calculate. And you see here that for their values for X, they got negative 59.2426. We got it dead on. And they got 0.8426. They just had a few more decimal places, but we also had that dead on. So that's excellent, excellent. You can also, again, use an app. The name of that app is Photomath. And using that app, you could actually take a picture, a picture of your formula of your work as early as this. You could take a photo of that right there, and you put it in the Photomath, and you make sure it's correct, and it will actually give you your values for X. It'll give you this and this. But again, you have to know how to interpret which one is right. So we have our value for X, 0.8426. Let's go back to the very beginning, right here, to the very beginning. X is equal to 0.8426, and X is a concentration. X represents change in concentration, so let's put the unit there. Molar. Okay, so now that we have that, we can find the equilibrium concentration of any one of these substances, of this, or this. Now, what they've asked us to find is the equilibrium concentration of HCl. So that is equal to 5.2 minus X. 5.2 minus X, which we found to be 0.8426. So 5.2 minus 0.8426 is equal to 4.3574 molar. And if we round it to 2 decimal places, it's equal to 4.36 molar. That is our answer. That is the equilibrium concentration of HCl. On the exam or on other problems, they may ask you for the equilibrium concentration of all of these substances. You would do it the exact same way. And for the sake of completion, let's go ahead and do it here. The equilibrium concentration of Cl2 is equal to X, which is equal to 0.84 molar. The equilibrium concentration of CHCl3 is equal to 5.6 plus X, which is equal to 5.6 plus 0.8426, which is equal to plus 0.8426, 6.44 molar. And finally, the equilibrium concentration of CCl4 is equal to 2.4 minus X, which is 2.4 minus 0.8426, 1.56 molar.